Good evening. So today I'd like to just talk about a final topic in electricity and magnetism, one of the final topics, which is inductors. An inductor is a device, it's actually just a coil of wire, it's a solenoid that we use in circuits sometimes. And so we call it an inductor, just like a resistor, a capacitor are circuit elements. An inductor is a circuit element. And inductors serve the same kind of purpose as a capacitor does for capacitor for electric field, inductor for a magnetic field. So remember what a capacitor does when you put it into a circuit. If you have a capacitor and you attach it to a battery, the capacitor will become charged. It'll charge up and it'll become charged. And in steady state, when the capacitor is fully charged, no current flows, but the capacitor stores an electric field. It stores electrical energy, and we know the energy stored in a capacitor is, for example, 1/2 Q delta V. So it stores energy in the electric field. An inductor is similar in that it stores magnetic field. So the capacitor stores an electric field or creates an electric field. A inductor stores magnetic field. So let's take the inductor, let me just redraw it down here, and attach it to a power supply. And imagine what's going to happen. What's going to happen is current will flow, and it doesn't, unlike the capacitor, it doesn't stop, but current flows through this coil, and the coil then stores magnetic field. So there will be a magnetic field in this coil. I believe that's the correct direction. Yeah, that's the correct direction of magnetic field. So there will be magnetic energy stored in that coil. And when there's a constant current in the circuit, there's going to be a constant magnetic field in the inductor, in the coil, in the solenoid. In this case, again, the solenoid is called the inductor. And by the way, the inductor is given a characteristic value called L, which is the inductance. I'm not going to get into all the details, like capacitance is Q, charge per unit potential difference. Inductance is N, the number of coils in the inductor, times phi, which is the flux, divided by the current through the inductor. But I'm not going to get into the details of why or whatever, but just to point out that this is a circuit element, and that when there's a constant current running in the circuit, remember the inductor, the wires in a circuit typically have resistance of zero, right? Resistance is zero, or they're small, or we ignore them. So there is no resistance to this current being set up in the circuit. And actually, so what I have drawn here really is, in a sense, a short circuit, because there's only resistanceless wires. Typically in any of these circuits, and we discussed the same thing with capacitors, you would also have a resistor in the circuit. But the resistance of the wires is zero, so the resistance of the inductance is zero. So at steady state, when the current is constant, the current through the circuit would be as if the inductor didn't exist, as if it wasn't there. But what I do want to point out about the inductor is that it does store magnetic field. It does store magnetic energy, so that it must have taken some energy to get the current going. And so what the inductor actually looks like is in charging up the circuit, in getting the current from zero to whatever I, if this is delta V, then in steady state, delta V is equal to I times R of the resistor. So therefore, I is equal to delta V over R. In order to get up to the current of delta V over R, the inductor took some energy, and so it slowed down the ramping up of the current. And so what inductors do is they impact circuits in which the current is changing. They don't have any impact on circuits which have constant current. They only impact circuits in which the current is changing. And again, I haven't really explained exactly what's going on here, but when we turn on the power supply here and the current is initially zero, the current doesn't immediately get up to I. It takes time to get there because it takes time to set up that magnetic field in the inductor. And so So what the inductor does is it acts like, one thing that it does is it acts like a resistance. It acts like a resistance to changing currents, and only to changing currents. It does not act like a resistance to constant currents, but it acts like a resistance to changing currents. I'm just trying to argue it qualitatively. I'm not going to show it quantitatively. So inductors are circuit elements that can be analyzed like capacitors and resistors, and we're not going to do that in this class. But just wanted to point that out, that inductor is another circuit element in our arsenal. So I've written down here what I just said, and let me explain this from the point of view of Lenz's law, right? From the point of view of Lenz's law, as the inductor sets up the magnetic field is increasing in the inductor. And so what that magnetic field, that increasing magnet, as the current goes from 0 to its maximum value, V over R, the magnetic field is increasing in the inductor. And that changing magnetic field, what it actually does is it induces a current in the coil, right? There's current coming from the power supply. There's a current coming from the power supply, but the current that's going through the coil, as the magnetic field gets bigger, right? This is just when you turn it on, right? As the current comes up from 0, as the magnetic field gets bigger, what it does is it induces another current in the coil that opposes the one that created it. So what happens is, as the current is increasing to the right, it is inducing a current to the left. And so it's slowing down the increase of current to the maximum, right, of V over R. So that's Lenz's law, right? This is the Lenz's law. Because of Lenz's law, that inductors, because they do have what's called this self-induction, they induce as you run a current through an inductor, as you run a current through a coil. If you run a current through a coil, there's a magnetic field that you set up in the coil, but if the current is changing, that magnetic field is changing. If that magnetic field is changing, that magnetic field will induce back in the coil, because it's a changing magnetic field in a coil, it will induce a current in the opposite direction, induced current. And so that acts like a resistance. It slows down, it reduces the amount of current that is passing through the coil, but you're still increasing the current. Eventually you will reach a steady state, but that's self-induction. It's an interesting phenomenon. In any case, okay.